All right, good afternoon, class. This is a little recording about these things called diatomic elements. So on that balancing sheet, you might have noticed elements are by themselves represented as molecules. So we see this with hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. And these I like to call the Magnificent Seven, right there. And I call them Magnificent Seven, well, because there's seven of them. And when they're an element in their pure form, they don't exist as atoms like the other elements do. Like we talked about magnesium. Magnesium is made of atoms, right? Pure magnesium metal that I gave you and we lit on fire is made of atoms. But the pure oxygen that reacted with it is made of oxygen molecules. But those molecules are only made of the same atom. So they were an element. Why do they do this? Well, this is actually a good little review for that thing we call Lewis structures. So if we consider first hydrogen. Okay, so hydrogen exists as an elemental form with the chemical formula H2. Why? Well, if you had pure hydrogen, that means you only have hydrogen atoms. And really simply, if two hydrogens were beside each other and one said, hey, I need an electron, and the other said, I need one too, they would share. So we're showing the Lewis structure here of the atoms, and then the final Lewis structure of the molecules. And we represent a shared pair of electrons with a dash. Very simple. Okay, and we can convert this to a thing called a ball and stick model. Okay, and what I call simple particle model, that's ball and stick, and that's Lewis. And then I call simple particle, but truthfully, it's actually called space fill. Ball and stick's good because it shows us the bond. And those are the same ones, the ones we can click together in class. However, however, in reality, space fill is closer to what really happens because the shells of the atoms merge, they fuse into one particle, and that's why it's called a molecule. So that's hydrogen. All right, what's up with oxygen? Now, all the green ones are going to be really easy because um, they're all halogens, but we're going to key in on oxygen now. So if we know oxygen and you know the Lewis structure of an atom, got to show you how to do it properly. 1, 2, 3, 4, 5. Now, strategically, I'm going to put the lone pair on the left side for this one. And let's say we had pure oxygen like that. And I can put that lone pair, we call them, if they're already paired up, they're called a lone pair or lone. And now this oxygen atom says to the other oxygen atom, hey, I need two electrons. And this other one says, hey, so do I. They don't actually say this, but let's pretend they're real people, little beings or something, because, chemistry is all about relationships. Okay. So what happens here is they are now each sharing two electrons. So this is what's called a double covalent bond. Covalent just means sharing outer electrons. Now, chemists like short forms, we're just going to call this a double bond. So they drop the word covalent, and you can just call it a double bond. And if that's a double bond, then this thing is called a single bond or single covalent bond. If you just say single bond to me, I know you're not talking about ionic bonds, which are different. Ionic bonds are just the attraction of ions between each other. Okay, so now we got the halogens. All right, and in our Hofbrinkel, that's going to be fluorine, bromine. Well, chlorine's actually technically next, if we're just going down the periodic table. So Cl2, sorry, let me do this. Now, this is oxygen. Let me go over here to oxide. Let's do this. Oxide is an ion, or we can use the word oxide when it's like in carbon dioxide. That's where that gets used as well. But that's another thing. If we're talking about the oxide ion, which we will shortly, We're going to have our 8 electrons because oxygen has stolen or picked up electrons from somebody else, and that thing has a charge of -2. So oxide ion, and this is the oxygen molecule. Now, again, we can use the word oxide in molecular compounds like carbon dioxide or carbon monoxide. We see that. Okay. So halogens. Okay. So if I say fluorine, I'm gonna do a bit of a speed run here. Okay. So I say fluorine. Okay. So that's F2. Well, if you think of the fluorine molecule, you can go like this. Well, fluorine has 7 electrons in its outside shell. And so one fluorine atom says to another, hey, do you want to share? Yeah, I'll share. And then we'll hang out until we can find a better deal. Okay. Now, this is not to be confused, this thing called fluoride ion. And that's when a fluorine atom gets its own electron. It doesn't have to share. Cool as that. And sometimes you'll see, a Lewis structure where they'll actually draw the gained electron a little bit different. Okay, so fluorine, and then there's this thing called chlorine, pure chlorine gas. You don't want to breathe that in. A chlorine atom has 7 electrons in the outside shell. And so does the other one, and they just say, hey, let's cut a deal. Well, here's chloride ion. And these are right out of that periodic table we did early on in the course, but we're sort of a callback to it right there. Okay, chloride ion, chlorine, and then bromine, pure bromine gas. So this is in their element form. And I'll just draw the Lewis structures for these. Okay, and then at the end, I'll draw the ball and stick because look, they're basically all following the same pattern. And I don't know why, but the chemistry geezers decided that the halogens are usually drawn in green color. Uh, Molybdenum does bromine in a bit of a different color, dark red for some reason, like deep, deep dark red. Okay, and then we got our bromide ion. And that's when a bromine atom picks up that extra electron. Got 7, and if somebody could give it an electron, it'll gladly take it and have a full valence shell. So there's a fluoride ion. So if you see the word fluorine or something plus fluorine, and we'll look at an example shortly, or chlorine or bromine, like that. Okay, and then of course iodine. So these are the halogens. And iodide ion is an I with the 8 electrons around it. So for nonmetals, you always want to show the 8 electrons around, square brackets, and a negative. For molecules, you show, for Lewis dots, you show the lone pairs. Okay, now if we do a space fill, or we'll do a ball and stick first. Okay, so we're just going to do a green one like that, green one like that, and then we'll just connect them with a single covalent bond like that. And then we can represent, and either of these will work, right? We could represent a halogen, space fill, what you guys would know as a simple particle like that. There you go. So those are just different models for these molecules, but now hopefully you understand why they do what they do. Okay, so that covers those dudes. Now nitrogen's fun. Because if we look at the nitrogen atom, right? Okay, so I can go 1, 2, 3, 4, 5. It's got 5 electrons in its outside shell, so it needs to gain 2. So I'm going to drop these lone pairs, these electrons as part of the lone pair, we call it. And then you got 3 bonding electrons, and the nitrogen goes, I need 3, and so do I. Okay, all right, bud, let's share. And nitrogen, N2, is extremely stable molecule because of this thing called the triple bond. All right, so these are the atoms. If you had pure nitrogen and you need 3 and I need 3, well, let's share. And they'll share equally until a better arrangement can be made. And nitrogen, again, is extremely stable molecule. 80% of the air we breathe is this very gas. So we're gonna go 1, 2, 3. So 3 dashes, and then we'll do our lone pairs there, and then they merge together. Okay. And again, if we're gonna do a ball and stick representation like this, there we go. And you can do ball and stick for your molecules when you're doing your chemical drawings. Okay, and I'll just overwrite that a bit. There we go. Okay, that's a little more mashed up. There we go. Okay, so that's ball and stick, but in reality, they don't They don't do that. They actually just merge. The atoms fuse together and they fuse into one particle called a molecule. All right, so that's why nitrogen gas, pure nitrogen in its elemental form, is N2. Now we got its buddy nitride. Okay, this is the ion. And again, nitride can be used in molecular naming, but we're going to just stick to this N. So let's think about this. 1, 2, 3, 4, 5. So if nitride could get uh, 3 electrons from someone, and I'll draw these as like little X's here. 1, 2, 3, so you can see them better. And so that thing has a charge of -3. Now I like to do a simple particle like that. There we go, 3 minus. Okay. And similarly up here, why do we always do chloride ions or any of these guys like a simple particle? Just there you go. Okay, as a charged particle. An oxide, of course, simple particle. Let's just draw one circle with a 2 minus in it. Okay. Whereas if we were to draw the oxygen model, here we go. It's going to be 2O2, but we're going to draw 2 bonds between it. There we go. And we call that the double covalent bond. But again, real life, those oxygen atoms, there aren't sticks between atoms. They fuse into one particle called a molecule that is made of 2 atoms. Okay, that's easy enough to get, I think, I hope. And one last note, that's called a triple bond. And triple bonds are neat, but they're very rare. Most of the time, they're single bonds and double bonds in real molecules. All right, so that's the diatomics. So whenever you see hydrogen by itself or oxygen, fluorine, nitrogen, Hofbrinkel, Hofbrincl. Okay, and all those exist as diatomic elements.